Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Tansu Daylan with us today. Hey, Tansu.
Hey, Francis. How are you?
I am doing well on this February 25th, 2021 is when we're doing this recording. So I'm doing quite well on this. It's turning into springtime a little bit here in Phoenix. The weather's starting to warm. We're getting a little bit of a kick from the wind. To push out some of the colder stuff. So starting to warm up here. How about you? Where are you at?
Well, I'm located in Boston, and last week we had a pretty bad cold. This week, I think it's getting much better. So I've started enjoying life again.
Okay. Okay. So are the trees starting to, let out some little leaves?
That may be a bit too early, but at least, yeah, I think I see people outside and enjoying the weather. So I think that's a good sign.
That's a good sign. Awesome. Very cool. Very cool. So what's your institution? Where are you?
I'm at MIT right now. And yeah, I've been a Cowley postdoctoral fellow for 3 years here.
Awesome. Congratulations. So are people going into the buildings at MIT, or are classes in full swing, or?
Well, so our building has been shut down since early March last year.
Mm-hmm.
And I think there's no immediate discussion of going back, but I think it will happen eventually.
No.
So I've been only back to campus 2 times, only to pick up stuff from the office.
Mm-hmm. Mm-hmm. Yeah, we just announced. So I'm at Arizona State, and they just announced the other day that we'll be going full in person for the fall. So that means August 2021. Of course, that assumes that the vaccines come out in volume like anticipated. But
yeah, it all depends on assumptions.
Right. So we'll see how it goes. So that'll be cool. Tansu, what do you like to do for research?
So I've worked on a bunch of problems so far, but lately for the last 3 years, I've been mostly focusing on discovery and characterization of planets beyond the solar system, so-called exoplanets. I've been basically working as part of the TESS team, leading a few projects. And I guess by now, anything in time domain astronomy kind of excites me because TESS can seed it and I have data for it. But when it comes to actually focusing on testable problems, I really am interested in testing how planet formation basically unfolds by using data we collect in exoplanet research. I'm very interested in atmospheric characterization of exoplanets and how these things actually can teach us something about our origins and whether we're alone in the universe.
Yes.
And time domain astronomy obviously is very broad. So I've also done some work on supernovae, finding these in the test data mostly, not on the theory side. But and during my PhD, I actually did a lot of other things like I worked on gamma ray data from Fermi, worked on the GEVXS. It's more morphological and spectral characterization and interpretation for dark matter origin, annihilating WIMPs. And my PhD thesis was actually on statistical methodology of sampling from a multidimensional space. So it's a sampling algorithm essentially that allows you to produce posterior distributions when your model actually has many dimensions. So it's got like submodels of different dimensionality.
Cool.
That's something I'm very much interested in still.
So you really have done a whole bunch in time domain astronomy, a whole variety of objects. That's very nice. And that is going to lead us to this very lovely, gorgeous AJ article on TESS discovery of a super Earth and 3 sub-Neptunes posted by a bright sunlight star HD 108236. And Tansu, take us away.
Yeah, thanks. So this is work I've done with a bunch of collaborators that you see currently on the screen, and with basically with the help of the broader TESS team. So this was a big effort that came out of the TESS mission. I can just very quickly introduce what TESS is. TESS is basically a spaceborne instrument that is surveying the sky for exoplanets, but obviously doing a lot of other things in the meantime. Its niche is exoplanets because it's got the photometric precision and wide field to search for these objects, but on the fly, it also collects data on other things like supernovae and tidal disruption events and astroseismology, etc. So yeah, so using TESS, basically we look for small exoplanets. The highlight of the TESS mission is to be able to find those exoplanets that orbit nearby and hence bright stars. And the nice thing about these is that we can use them for further characterization. This can be orbital architecture characterization. This can be atmospheric characterization, and also bulk composition characterization, bulk characterization. Basically, there are a couple of unsolved problems in exoplanet science. For example, we would like to understand the difference between a super-Earth, a terrestrial super-Earth, and a sub-Neptune. What is the boundary? What is the cause of the radius valley in the current insolation versus radius distribution of exoplanets? As well as whether our solar system is typical or not. Why do we not see a super-Earth or a sub-Neptune in our own solar system? Such questions can be answered only if you collect data on enough systems that are amenable to detailed characterization. And this definitely requires mass measurements and radius measurements. So basically TESS produces this golden sample of exoplanets across the sky, basically. And this paper is about a highlight from the TESS mission. In fact, it is one of the typical discoveries that we were expecting from TESS. You have a question? Oh, yeah. So basically, this highlight is in the form of a planetary system called HD 108236. The very fact that it's got an HD number will tell the interested audience that it's a bright star. Its visual magnitude 9.2. And well, in the context of all the stars on the sky, obviously it's not a naked star. It's not too bright or exceptionally bright. But when you put it in the context of systems with multiple transiting planets, it's one of the brighter ones. And when you put it in the context of systems with more than 3 transiting exoplanets, it's one of the brightest ones. If you actually constrain that definition to that of sun-like stars, G-type, then it is the brightest star on the sky to be transited by at least 4 planets. Nice. And on top of that, these are small planets, small in the TESS definition. Basically, when we say small, especially in the TESS jargon, we mean level 1 science requirement, which means smaller than Neptune, which has a radius of about 3.8 Earth radius. So we're talking like less than 4 roughly. And the nice thing about this is that because the star is bright, the planets are amenable, first of all, to mass measurements and then to atmospheric characterization. And above all, I mean, there are many other systems where this is actually the case, but what's unique about this is that all of these planets are so, which means that you can do it for all the planets in the same system and then compare them. In the exoplanet science, one thing that we get confused a lot about is the fact that stars behave in many ways that we cannot anticipate or model perfectly. For example, every star has a very unknown, well, every field star has a very well unknown age. And also initial composition, like metallicity is not very well known, or the uncertainties can be fairly large, which means that when we try to compare planets across different stars, like belonging to different stars, it is very hard to put them on the same scale. Right. And it's also very hard to then produce a population model of exoplanets. So then one likes to basically find systems where there are many planets, all of which are actually amenable to detailed characterization. So you can shunt out basically those uncertainties or marginalize over, in the Bayesian sense, those uncertainties that come from unknowns about the star itself. So by having such systems, you're essentially controlling for the age of the star, the stellar insolation history of the star, not the amplitude. Obviously, the amplitude is going to be different for different planets. You are controlling for the type of the star, the stellar type, the effective temperature. And you're also controlling for the composition of the initial protoplanetary disk that actually gave rise to the planets.
Right.
So by having these controlled mechanisms, you can very precisely and accurately actually study planet formation and evolution, for example, radius mass relation as a function of stellar insolation. This then becomes basically a golden sample for testing theories of planet formation and evolution. This is basically the main motivation for searching for planets or planetary systems, multiplanetary systems like HD 108-236. And there are only a few of those. And I just, as I said, this particular system, the TOI 1233 system, is the brightest such sun-like multiplanetary system where we have more than 3 transiting exoplanets. As a kind of context, just to build more context around this, Cheops, which is basically the European analog of TESS. However, the science cases are a bit different. TESS is like a discovery machine and Cheops is like a characterization machine. They are working in tandem, and Cheops actually observed this system right after our TOI, or actually even before our TOI alert went out through private communication. And they actually observed the system, and they even published a paper finding yet another planet in the same system, which is great because, first of all, it is a nice example of how the two telescopes can actually work in collaboration with each other and produce a spectacular science result, but also from a more practical point of view, now our system actually is turning into a really rich multiplanetary system, compact multiplanetary system, and its science potential is growing, so that we have this 5th planet in the same system. So we can, if you like, we can start going through some details. I guess I've pretty much talked about the abstract, but maybe just to give some numbers, the orbital periods of these planets are roughly about 3.8 days, and then the outer ones are 6.2, 14.2 and 19.6 days. The one that Cheops recovered, that's 29.5 days. So we are talking about a compact system, and the radii are all below 4 Earth radii. The innermost one being 1.6 roughly, which is essentially a super Earth at that insolation. And the other 3 are basically sub-Neptunes. Well, the other 4, including the Cheops detection more recently, they're all sub-Neptunes. The Cheops detection might also, based on some atmospheric modeling, can also be terrestrial, but I think that is not a very well answered question as of now. Obviously, the final word on that will be precise mass measurements on these systems. So far, there has been one publication after our discovery trying to measure the masses of these systems, and that's Johanna's paper from the TESS Magellan survey, and that has not produced accurate masses for all planets, and some masses are still going negative. So we just need more data, PRV wise, precision radial velocity wise. But it is work in progress, and COVID is not helping, obviously. This is a southern target. It's actually negative 50 dec roughly, which means that only things in Chile can actually see it. And COVID has been hitting Chilean observatories in a few ways, I would say. So that has not yet been possible to a great extent. Okay, yeah. So if you have any questions so far.
I just wanted to highlight the crazy small uncertainties here, right? I mean, we have many digits of precision on these numbers. It's just wild.
Right. So the precision on the periods is thanks to basically the fact that we have a large baseline. That baseline produces small uncertainties on the periods because we have more than one transit detection. Once you have two, that already sets the scale for which you can constrain the periods. But the radius uncertainties is, I think, even more spectacular because you're really making measurement of about a millimag, and even for the smaller ones, it's actually sub-millimag. So that I think is just speaking to the potential of space-based surveys, photometry. Right, so let's go to maybe the table one just to set the stage. Yeah, it's called TOI 1233. That stands for TESS Objects of Interest 1233. We give out an ID to all the TESS detections, and this was the 1233. Or obviously, these are not like sometimes they can like the TOI number does not necessarily correspond to a detection date. They are sometimes out of order. The reason I'm emphasizing this is because this is such a case for 1233. 1233 was alerted a bit later than usual, and that's because we waited for an additional analysis that came from the NASA Ames pipeline. And the alert was actually later than usual. But then that you have the tick ID. I won't go through all the details in the table one, but it just gives you an idea of how bright the system is. If you just want to look at the V magnitude, that's 9.25. And yeah, it's a southern target. And the distance is about 64 parsecs. So it's nearby, not exceptionally nearby, but definitely since it's a sun-like star, it makes it bright. Yeah, so then you have the stellar characterization, SED fit to the right in figure one. So we basically, as part of this work, we characterized the star both through model independent and model dependent ways, arrived at a consistent result, and we concluded that this is basically a sun-like star, slightly smaller than, it's about 89% of the radius of the sun. Temperature-wise, it's so close, almost the same temperature, I would say, and it's a bit, its metallicity is slightly subsolar, but otherwise very similar to our sun. And then going down, we can look at, I guess, the first data from TESS. So if you just go to the next page. Right, so we have the stellar characteristics. We will have to skip that just to conserve some time for later discussion. Yeah, so this is the detection data. So we've got two sectors. If you just go to the previous figure, that was the detection figure. Let's see, yes, this one, figure two. So in the figure two, you see basically the transits of different planets color-coded. So basically, you've got B, C, D, and E. The innermost one, hence the smallest period, is B, and the outermost, from which we only got two transits, is E. And then F is not highlighted here, but one of the transits of F was actually on top of the first transit of E. And then the second one was a single transit for us. Basically, that was just, I think, after 1615, just after C transit. So basically, and then obviously the QOPS team actually observed serendipitously the transit of F, and then they phase folded and realized that there is actually another planet in the same system. So going further down, I think there will be a bunch of plots that allowed us to actually vet these planet candidates and show that this is basically, this is not a false positive. That's actually a pretty long pipeline that basically starts with some reconnaissance data. I will just give a quick summary because we will not have time to go through the details. It starts with reconnaissance spectroscopy just to show that it is not a binary system. So that you can see actually, if you go down, there is going to be some RV radial velocity data that shows that the star doesn't have a massive companion. Otherwise, it would, yes. So this plot basically shows that the differential radial velocity is consistent with planetary nature. We initially collected data from the LCO network using NRES and then Chiron. And then eventually collected the PFS data as well and showed that the variation in RV is definitely substellar. So this made us confident that we are looking at a multiplanetary system. But then we also had to check individual transits to make sure that at least one of the transits or periodic transits was not coming from a nearby eclipsing binary. That can always happen.
Yeah.
So that we did using MERTH and LCO network again, if you go down. And then we also collected high resolution imaging to make sure that there was no nearby bright companion to the star that was conducted using SOAR, HRCAM, and Gemini. And this basically showed a delta mag of about 5. So that's about 1 to 100, which is spectacular, which means that you don't have a bright neighbor, stellar neighbor. And then finally, you'll see, I think, the table that shows the SG1 data. SG1 means seeing limited photometry in the TESS lingo. It basically means that we checked for nearby eclipsing binaries to show that each individual transit was not a contamination from a nearby star. For those who are not familiar with TESS, this may not feel obvious. The reason why we need this is because TESS pixels are large, 20 arc seconds on the side. This is MERTH follow-up, just one example from our seeing limited follow-up of the system. So the TESS pixels are large, which means that when you have and when you do aperture photometry to find these transits, they may actually be coming from anywhere within an arc minute or so, depending on how bright your star is. So you have to check basically the whole field to make sure that other nearby eclipsing binaries don't mimic one of your transit signals. So eventually we also collected some data to follow up on the system. That's what you see in the figure below with the red points. That's, I think, from the planet D. Yeah. So and then basically that was the end of our follow-up. We started basically working on the paper, made sure that the system was stable. By the way, that was one of the checks. That's going to appear pretty much at the end of the paper. We basically checked that the orbits by simulation, and by the simulation, we checked that the orbits were dynamically stable, which was confirmed. And then, well, with such multiplanetary systems, you have to check that's the case, because there are many configurations that would not give you a stable system. So this is almost like a sanity check, just to make sure that what you get out of the photometric model actually makes sense dynamically. So that's what we did. So if you go down further, you'll see, I think, the phase curve now. The phase curve is essentially what we get kind of in the beginning. So this is not chronological, but yeah, so these phase curves are essentially light curves. Once you detect a periodic train of boxes in your data, you phase fold and get these pictures. And this basically, you can see that the depth essentially is increasing, going from B to E, which is an indication that the radii is actually increasing. And these are, as you can see, all sub-millimag or at most a millimag, which means that you can only do this from space. And then if you go further down, yeah, this is just a pretty picture of the system. And then you've got the radii, which is important. One of the planets, planet B, is actually in the so-called radius valley, or close to being in the radius valley, but it's actually on the super Earth side, which means that it's very likely that it's actually terrestrial. And the other three probably have volatile envelopes around them with a different fraction of hydrogen and helium. Probably E has the largest envelope. And if you go further down, this basically, I'll try to go fast here. So this basically is on the right, you see the equation for TSM, which is the transmission spectroscopy metric, which is bringing the discussion to the atmospheric characterization potential of this system. And there will be a plot that will show down below that the TSMs of these planets are pretty high. They're not the highest, but again, I think going back to my previous point, oh, this is about the brightness of the star. I think I've already motivated this. The brightest star that has a multiplanetary system is actually Kepler 444, but that is not Sun-like. And HIP 41378 Andrews system, that's also not Sun-like. So basically HD 108-236 is, well, this is obviously outdated. Counting the Cheops detection, now we are up to 5 transiting planets in the same system, but basically we are not as bright as those two. However, again, HD 108-236 is unique in the context of Sun-like stars. So Sun-like stars, we like Sun-like stars from a different direction, because we think life exists around a planet, around a Sun-like star or sun. So we think that when it comes to outer companions, habitability potential of outer companions, if there are outer companions of HD 108-236, which will show up in potentially future data, photometric follow-up data, then we might even discuss habitability aspects of the outer companions of these planets.
Cool.
Right, so if you go further down, there will be just a bunch of plots showing the potential of the system. Right, these two are important for the atmospheric characterization potential of the 4 planets. The top one is showing the TSM of the top list, and you can see that they're among the top 20 of those that have good mass measurements. And then down below, you see the equilibrium temperature versus the radius of the planet. And basically, it's showing the span in this fundamental plane of the atmospheric characterization science, that we span a broad range. And this allows, again, controlled experiments in atmospheric characterization. So if we go down below, we can wrap up just to conserve more time. Yeah, these are basically just the planetary properties that came out of the FIT. By the way, just as an advertisement, we used LSFitter, which is a code that Max and I co-developed, which basically does modeling of photometric and radial velocity data. And it's a generic pipeline, it's user-friendly, and it's been used by many publications so far, excluding our own.
It's open source?
It is open source, yes. We even welcome, contributions.
Awesome.
And so there's also a plot about the TTVs, transit timing variations, and there is none. And I just checked that Cheops paper also finds a consistent result. They don't also see, but I mean, Cheops measurements were also very close to our detection, which means that we just did not collect enough baseline. So TESS will be reobserving the system very soon, in fact, this spring. It's a spring star, by the way. So it's the best time to observe it if you're a ground observer, and if you want to contribute to observing the system, this is the right time, or the right time is approaching.
Yep.
So this TTV plot basically means that implies that there is no TTV yet, and we don't expect a strong TTV because no planet pair that we found was in perfect mean motion or very strongly close to a mean motion resonance. The distances are ordered like percent, and that obviously only leaves the possibility of a chopping signal, which we will be looking for very soon in the test data. And as part of this work, we also speculated, at best, for the dynamical gap for the existence of an additional transiting or non-transiting planet in the dynamical gap between planets C and D. If you look at the orbital period ratios, you see that there's a big gap, and you can certainly fit a three-body resonance there. So the relevant orbital periods would be roughly 9.3 or about 9.2 days. And we've searched for additional planets there, haven't found anything, but as TESS and other instruments follow up the system, we might be bound to finding more planets in that gap.
Wow.
So if you go down, I think the last figure will be about the dynamical stability of the system.
There's your eccentricities.
Yeah, so exactly. This is basically a plot of the eccentricity from the dynamical simulation, showing that it's dynamically stable. The eccentricity doesn't grow as a function of time. This is actually a histogram, but so basically that concludes the figures. And overall, just to sum up, I think we now have a very opportune system for testing various models of planet formation and evolution and atmospheric escape. Study atmospheric escape as a function of, for example, insolation. I think this would be a good system to do that within the same system. And we are obviously tuned to looking for outer companions to see if this is going to be a system with even more planets and potentially planets that might be close to the habitable zone.
Very cool. Very cool. Tansu, thank you. So you hinted at several near future directions. So why don't I ask you to look in your crystal ball and, even on longer time scales than this coming spring, where if people want to contribute, but what about on like 5-year time scales or something of that order? Where should the community go, maybe on this system or on systems like this?
Right. So yes, at a short time scale, I think there's a lot to do for this system to just fill in the blanks of the characterization of this system. But at a broader scale, 5 years later, I guess 5 years later, TESS might still be alive and collecting more data, producing even better systems potentially. But eventually, we will have a pool from the TESS mission that are pool of exoplanets from the TESS mission that are amenable to detailed characterization. So I see this multidimensionally. So first dimension is constraining the bulk composition, especially in the mass radius plane of small planets, showing us, for example, what is the insolation dependence of the radius mass relation. It's a question that I'm very interested in answering using systems like this, and also stellar type dependence of the radius mass relation, and also on the atmospheric characterization side, doing the same as a function of stellar type and potentially even metallicity, study the atmospheric composition difference of planets as a function of insolation. One thing that I did not discuss so far is actually the fact that using atmospheric characterization, we can also break degeneracies in the bulk composition. So sometimes, just to distinguish is, for example, a super Earth from a sub-Neptune, the radius and mass themselves may not be enough. So basically, we then need atmospheric measurements to tell apart a super Earth from a sub-Neptune. So then further atmospheric characterization of these systems and systems alike might then give us a picture to do that in a broad sense, not just using a few numbers to characterize a planet, but rather a spectrum of well-measured quantities to pin down how these quantities both depend on the insolation as well as the broader initial conditions of the star formation.
Right. Very nice. Very nice. Lots of exciting stuff coming over the next couple of years. Super great. All right, everyone, that'll do. I want to thank you so much. Tansu, again, thank you so much.
Thank you. Yeah, thanks for the invitation. And this was a great experience.
Yeah, it was lovely, lovely. Go over the article. Okay, everyone, we'll see you on the next one. Thank you. Bye-bye.